In your A-level chemistry, there are lots of calculations to do, but there are also quite a few key facts to memorise, and also conventions like writing concentrations using square brackets. Many of these are things that you would have met during GCSE chemistry, but to be honest, equilibrium is one of the hardest topics in GCSE chemistry, and lots of people finish year 11 still having a lot of misconceptions about the subject. This video is the 6th in an AS chemistry revision series to help you to ensure that you've thoroughly learned the facts that are listed in your specification, so that you can then go on and do those numerical calculations without having your factual recall let you down. There's a link in the description below to all of the questions, so you can download a worksheet, answer these, and then use this video to check your answers. Chemical equilibrium is reached when in a reaction the concentrations of the reactants and the products are unchanging. I just want to point out that doesn't mean that they are the same as each other. In fact, they very rarely are. And there's a whole branch of chemical industry which is based on trying to maximise the concentration of the products. In other words, maximise the yield so that you can make as much money as possible. I think this misconception probably comes about because when most people meet equilibrium for the first time, they're doing so in GCSE biology talking about diffusion, which isn't actually a chemical equilibrium at all, and also it's a very rare example of an equilibrium in that it does have equal concentrations on both sides of a membrane or in both parts of an area. The reason that that equilibrium is reached is because the forward and the reverse reactions are occurring at equal rates. In order for a chemical reaction to reach equilibrium, firstly it needs to be reversible, but also we need to have those equal rates of forward and reverse reaction, and it needs to be occurring in a closed system. In other words, no matter and no energy can get in or out. Le Chatelier's principle tells us that a system at equilibrium will shift in order to counteract a change. In other words, if I add a reagent, then the equilibrium will shift to remove it. If I increase the temperature, then the equilibrium will shift to lower the temperature. And if I decrease the pressure, then the system will shift in order to increase the pressure and restore the original conditions. A homogeneous reaction is one in which all reactants and all products are in the same phase. As you probably recall from GCSE, the Haber process is the industrial process where nitrogen and hydrogen are combined in order to make ammonia, which is really useful as a fertiliser and for making chemical weapons and all sorts of other things. So in this process, 1 mole of nitrogen combines with 3 moles of hydrogen in order to make 2 moles of ammonia. This is a process where the forward reaction is exothermic, and that means that if you increase the temperature, this decreases the yield. As we know, in any system that is at equilibrium, if it's a closed system, then if we alter something, the system will shift to counteract the change. Now here we're heating, so that's obviously going to favour the endothermic reaction, which here is the reverse reaction, and therefore the equilibrium shifts to the left. In spite of this, we don't use a low temperature for the Haber process because although this would increase the yield, it will decrease the rate because all of the particles have less energy and therefore there are fewer successful collisions. If you increase the pressure of the Haber process, then you will increase the yield. And this is the case because, again, the system is going to shift to counteract the change. And here that means trying to decrease the pressure again. So because there are fewer molecules on the right-hand side of the equation, because we've only got 2 moles of ammonia compared to 1 mole of nitrogen and 3 moles of hydrogen, the forward reaction is therefore favoured and the equilibrium is going to shift to the right. So we do use a high pressure for the Haber process, but not an extremely high pressure for 2 key reasons. One being the cost of raising that pressure and the other being the safety aspect. In this next question, we're looking at the impact of adding a reactant, in this case A. So this is going to increase the yield of the product C. And the reason for this, again, we come back to Le Chatelier's principle, which tells us that the system is going to shift to counteract the change. So here the change was that we added A and we want to remove it. And the forward reaction is the one that removes A, so it's the forward reaction that is favoured, and therefore equilibrium shifts to the right. Adding a catalyst won't affect the position of equilibrium, and this is because the forward and reverse reactions are sped up by the same amount. So overall, there's no change. Finally, we're looking briefly at how we can write these Kc expressions, which are then going to lead into the calculations that you do as part of this equilibrium unit. So concentration is denoted using square brackets. And it's really important that you only use those square brackets when you're talking about concentration. So if you're actually in year 13 but you're revising the year 12 content, bear that in mind when you start looking at your KP calculations, that they are looking at pressures and partial pressures, not concentrations, and so you shouldn't use square brackets in that instance. If we were going to write an expression for Kc for this reaction, then we know that the products need to go on top and the powers are going to tell us how many moles of each substance there are. So you should have an expression that looks like this. We've got square brackets around each letter to show we're talking concentration, and then you've got a power of 3 for D because there are 3 moles of it, and a power of 2 for B because there are 2 moles of it. When we start thinking about what will affect Kc, temperature is the only one that is going to have an impact. So if we change the concentration, then equilibrium will shift in order to keep Kc the same. And if we add a catalyst, then we know that doesn't ever have any impact on equilibrium, and therefore it won't affect Kc. Thank you very much for watching, and I hope that you found this a useful contribution to your revision for A-level chemistry. If you did find it useful, then don't forget to look up the other videos in the series and like and subscribe for more A-level chemistry videos coming soon.